Thank you for visiting our website. Today we present the practice of immobilization of alpha-amylase enzyme from microorganisms Saccharomyces cerevisiae, Bacillus subtilis, and Aspergillus oryzae. Enzymes are biological catalysts consist of proteins which participate in many chemical reactions occurring in living things. The processes catalyzed by enzymes in the industry are increasingly numerous since present a series of adaptations over conventional non-biological catalysts. Immobilization of enzymes can dramatically improve their stability and the biocatalysts available for the industrial production of chemicals, drugs and foods, waste treatment, clinical analysis and disease treatment, and many other applications. The immobilization of enzymes is a process in which the enzyme is confined or located in a defined region of the space to give rise to insoluble forms that retain their catalytic activity and that can be repeatedly reused. Various techniques for the immobilization of cells have been proposed. In general, immobilization methods are usually classified into two broad categories: one, physical retention, and two, chemical union. We have two methods of immobilization of enzymes by physical retention: one, entrapment; two, inclusion in membranes. We have two methods of immobilization of enzymes by chemical union: one, union to support, absorption, unique and union covalent; two, reticulate, reticulate pure and co-reticulate. Recent use of polysaccharide, gel traps, or encapsulation, they have become a challenging method, and the use of alginate gel beds stands out as the most promising and versatile method yet. The entrapment technique consists of a physical retention of the enzymes in the polymers or polymers of the polyacrylamide type, collagen, alginate, or polyurethane resins. Alginate has been used because of its multiple advantages for both consumption human as versatility in industrial applications.
More the sodium salt has been found due to its high solubility in cold water and characteristic transition. So gel for instantaneous and irreversible to the calcium ion. Calcium chloride can become an important source of calcium ions for a solution, as is the case of precipitation, because some chemical compounds together with calcium lack solubility. It's for this reason that they are used coagulants for some procedures in the bioprocess, such as the immobilization enzymes. During the process of immobilization of enzymes, alginate is used mainly as a component of the membrane, and the combination with divalent ions such as calcium to induce gelation. This interaction and ion cross-linking takes place between the calcium ions and the glucuronic acid units of the sodium alginate, giving rise to a get known as the Xbox model. In contact with calcium ions, sodium alginate for a gel instantly. The ions are still diffusing in it, making the gel harden over time. Vapor entering the drop as sodium alginate in contact with calcium brought to the instantaneous gelation of the same takes place, obtaining a membrane or cover of calcium alginate that is insoluble in water but permeable. Specific objectives are determining the optimal concentration of sodium alginate and calcium chloride, get enough beans with enzyme for protein quantification, and determine a viable technique to dissolve the beans with enzyme for forest analysis. Of the alpha-amylase enzyme, the methodology described in diagram 1 was
It was being reported that porosity of calcium alginate beds depend upon the alginate type and the gelling agent concentration. Sodium alginate is an atomic polysaccharide. It was said that it contains ions with electric chains negative. Its structure is shown in the figure 2, where presence of sodium ions. When the sodium alginate mixed with the enzyme alpha-amylase comes into contact with chloride of calcium, the sodium ions in sodium alginate are replaced by calcium ions, thus forming different links with the alginate. Calcium is able to form two bonds, while that sodium can only form one. Due to this interaction, the gel stiffness will depend on how long they are in contact with has a concentration of calcium chloride, which in this case it was 0.3 molar. That is the amount of available calcium ions in the middle. During the practice, we use a concentration of 2% sodium alginate. Gargi 2003 mentioned that a lower effectiveness of immobilization in the case of a sodium alginate solution of lower percentage could be due a higher pore size and consequently to a greater leakage in the enzyme from the matrix. However, using concentration above 3%, the pore size will be smaller, so that the enzyme does not manage to enter the matrix. To carry out the Bradford test on the alginate enzyme beds, to know the enzyme that remained immobilized, they underwent change in pH in a neutral pH phosphate buffer pH 7. Science investigate calcium alginate with enzyme is very sensitive to change of pH, and in turn the beds maintain their shape at low pH. The results obtained the Bradford test in the calcium chloride solution and the first washing to the beds with enzyme alpha-amylase from Bacillus subtilis, Saccharomyces cerevisiae, and Aspergillus oryzae are shown below, table 2 and 3 respectively. Quantification of the immobilizing enzyme was performed to have the approximate concentration in 7 beds with enzyme alpha-amylase from Saccharomyces cerevisiae in table 4. For the quantification of alpha-amylase from Bacillus subtilis, the results obtained are in the table 5. For the quantification of alpha-amylase from Aspergillus oryzae, the results obtained are in the table 6. Then, based on the results of the Bradford test, we perform the enzyme balance for each immobilization procedure of sample enzyme from Saccharomyces cerevisiae, Bacillus subtilis, and Aspergillus oryzae.
In this diagram 2 shows the process of immobilization of alpha-amylase enzyme from Saccharomyces cerevisiae In the diagram 3 shows the process of immobilization of alpha-amylase enzyme from Bacillus subtilis. In the diagram 4 shows the process of immobilization of alpha-amylase enzyme from Aspergillus oryzae. For each balance, we made a global balance for applying the general equation of balance for the enzyme they interacted in the process. When we got the global balance in the next table, we calculate the microgram enzyme of the sample initial and final. For the calculation of efficiency, we use the following equation. In the table 8 are the result the efficiency of each process. Taking into account the result obtained from the efficiency for the immobilization of alpha-amylase from Saccharomyces cerevisiae, 59% higher immobilization efficiency could not be attained due to some leakage of the enzyme into the solution. Although in practice, reducing the size of the pores can reduce leakage, some initial leakage of the enzyme molecule is certain to occur, target at 23. Ideally, the entire amount the enzyme using in the process should be immobilized. However, it is not like that. The following table 9 shows the theoretical amount of enzyme immobilized in microgram for bends, which is compared with the table 10 where we have the amount of experimental immobilized enzyme per bends. With this, the percentage of non-immobilized enzyme loss is obtained the table 11 for the equation previous to the table. Now, we must take into account the enzyme losses during the experimentation. For example, in the calcium chloride solution, the weathered washes and the losses that remained stored in the storage that were occupied to make the bends. In spite of that, a very effective immobilization was not achieved. The enzyme that was immobilized from Bacillus subtilis and Aspergillus oryzae present a high degree of activity reflected in the efficiency of 73 and 77% respectively. In conclusion, alpha-amylase was immobilized from Saccharomyces cerevisiae, Bacillus subtilis, and Aspergillus oryzae by means of the entrapment technique using sodium alginate. The optimal concentration of sodium alginate and calcium chloride were determined having concentration of 2% and 0.3 molar respectively for the greater efficiency of the immobilization process. Bradford test was carried out to know the amount of enzyme immobilized and the one that remained unimmobilized. The global balance were made for each process in order to know the total enzyme loss during the experimentation. The efficiency of the immobilization process for alpha-amylase from Saccharomyces cerevisiae is 59%. For the immobilization process for alpha-amylase from Bacillus subtilis is 73%. In the case of the immobilization efficiency of the commercial enzyme is turned out to be the highest with a result of 77%. Thank you for visiting our page. In your we find more information about immobilization of enzyme.